Hello everyone and welcome. Today's experiment is called Whirling of Shafts. And the main objective of this experiment is to investigate the whirling behavior of the shafts. As we have already discussed, the shafts have some certain critical speeds at which the whirling phenomena can be seen, and this is also called mechanical resonance. And today we're going to take a look at first two modes of these two shafts, one of which has 3.15 millimeter diameter and the other one has 6.35 millimeter diameter, and both have a length of 91.44 centimeter length, and these parameters will be given to you later. So let's first take a look at the experimental setup. So this is the whirling of shafts apparatus, and let us open the inside. We have the motor on this end, and we have here ball and socket joint that you can see. So it can change its angles, but it cannot move in this direction. Here we have a displacement limiter that is put there for a purpose, because we don't want to we want to limit the transverse displacement of the shaft so that we will not have this catastrophic failure, plastic deformation of the shaft as much as possible. And also here we have a self-aligning bearing. It aligns itself and it does not let you move. Inside this housing you cannot move it any further. It's fixed to this housing, but this housing can move in this outer extra housing. So we're going to just push it to the left and connect the shafts, and then give the input via this speed controller, which is actually secured by this one. Before putting that in, you cannot turn on the speed control unit. So after we connect the shafts to this end, ball and socket joint end, and self-aligning end, where we actually secure and tighten it with a nut, because they have threads on this support side. So we put a nut here. And we connect the shaft securely, and after that we close the lid and start to increase the speed. So how do we measure the rotational frequency in situ? So we do that with this tachometer, which actually turns on when you press it, and when you hold it, it has some laser, as you can see. We're going to put that laser here, right onto this. And when it rotates, as you can see, there is a white marking, as you can see here. As it hits the white marking, it is reflected back to the tachometer, and the tachometer measures the rotating frequency of this motor with a unit RPM, rotations per minute. So this is important. So this is our experimental setup. We have two shafts, two ends providing us the pin-pin boundary conditions, and we have the motor end, we have the other support, we have the engine control unit, speed control unit, and then we have the measurement device, which is the digital tachometer, and we have the apparatus. So let's connect some shafts and get some readings and see how we can read and measure, let's say. As you can see, we have securely fixed our shafts to both ends, having pin-pin boundary conditions. And now let's try to get some measurements. I'm going to put my camera down here so that you'll be able to see the measurement device. With one hand, okay, let's move it a little bit back here. Okay, so you can see the number. So I will press and hold it, so we have the laser. So we don't have any reading, these are wrong readings actually. So okay, I will start to rotate the shaft, and you will start to hear the shaft rotating. We are getting some measurements. Okay, we start to get measurements now. And now I'm increasing the speed slowly. And this is how we take the measurements. And about some RPM, as you can see, it became loud. And now it's even faster. So this is actually how we measure with this device. Let's stop it and let's get back to some better angle so that you will be able to see the half sine and full sine waves better. Okay, now let's start the experiment. But before getting into the experiment, we have to first calculate the natural frequencies theoretically so that we might have an understanding about at around where we expect our measurements to be. And we expect our first mode measurement to be at around 450 or 500 RPM. And for the second mode, I expect it to be between 1600 and 1700. These expectations are important because if you don't do these, you just move back and forth, try to look for the mode shapes, and you lose time. But when you have some expectations beforehand, you can at least decrease the amount of frequencies at which you try to find these mode shapes. So that's why I did the calculations, and you have to do the calculations always beforehand if you can. So let us start our experiment. I turn on my device, measurement device, and now I start to rotate the motor. I have to be very careful because it's not that precise, and my measurement device does not precisely measure it as well. I have to be very careful about my inputs. Okay, we're at 200. 250, 260. We're moving a little bit faster. 320. 380. Okay, I'm at around 400. And when I increase to 450, you'll be able to see some peak deflections right in the middle of the shaft, which is actually the first one. And you'll be able to see the half sine. I'll try to move as slow as possible so that you can see it. Okay, so you can see gradual increase. Yeah, deflection, and it's gone. Because we passed the first mode. That was the first mode actually. And now we can move fast because we know that the second mode will be at around 1600. So we can move fast until we reach 1400, 1500. And then we slow down. Okay, we're at around 1400. I expect the sine wave to be seen at around 1600, 1700. So we're at 1500, and we're close to seeing the sine wave. So in order to see the full sine, please take a look at these 2 points where you will be able to see the peak points of the sine wave, full sine. And be careful, here it comes. See, we have the sine wave, and we pass it. As an engineer, you have to always avoid these natural frequencies because they can be drastic for the structure. So you have to always make sure that your structure, in this case your shaft, works in a range in which the natural frequencies are not passed slowly or are not being passed at all. So you have to design it very carefully. Okay, I'm at 2000, and now I'll slow down, and you'll be able to see the second mode again. 1000. And see, this is the sine the middle, see, deflection increases drastically. And as I slow it down, it vanished. So we pass the first mode again. So, this is the whirling of shafts, and I have shown you the shaft with 3.15 millimeter. Now, let's get to the thicker one, where we'll be able to see the modes easily. Now, we are with the second shaft with 6.35 millimeter diameter, which is as twice thick as the first one, and we'll be able to easily see, even easier than the thinnest one, thinner one, we'll be able to easily see the first mode and the second mode, but we will not reach the second mode because it's pretty thick and relatively heavy. It will have a lot of eccentricity and a lot of centrifugal forces, and it may drastically fail, as can be seen here when you reach the second mode. By the way, beforehand calculations show us that we should expect our first mode and second mode measurements to be about 750 and 800 RPM for the first mode and 3200 RPM at around 3200 RPM for the second mode. But we will not reach 3200. At around 2500, 2600, maybe 2700, you'll be able to see the starting of the full sine, but I will not go any further in order to protect our shafts and our whirling of shaft apparatus. So let's start our experiment. I turn on my measurement device and now I start to increase the speed slowly. Okay, it's not turned on. You have to make sure that it's turned on. Okay, we started. You have to first take a look at your tachometer and you have to make sure that your measurements are relatively stable. It will move up and down plus or minus 10 RPM, but it should not move any further back and forth. We're at 250. As I said earlier, I expect it to be at around 700, 800, 750 RPM. So we're at 300, we move faster. I'm not going to stay in the first mode very long. So please take a look at the middle. And I'll increase. See, this is the first mode. And I'll just pause it. I should not stay there too much. And now, I increase it a little further. And I will increase it suddenly so that you can see the sine wave, and then I'll just decrease it quite fast. Three, two, one. Please take a look at the peaks for the full sine mode. Here it comes. Let's try it again. Here it comes. See? Let's try it again. Here it comes. Yeah. So that was the second mode. I do not want to play with it any further because I might damage the shaft pretty easily. And as you can already see, it has some initial deflections already. So I should not increase this plastic deformation, and I should end this experiment right now. So I will give you, I did some measurements beforehand. I did this experiment before, and I get some values that you will use it in your experiment reports. For the second one, we did not reach the second mode. For the cylinder, for the shaft with 6.35 millimeter diameter, we did not reach the second mode. We just get close to it, so that you will have pretty high errors, and that is because of this. We did not reach it. So keep that in mind. And I would like to talk about the roots of errors briefly. So first of all, we secure the system with a bolt nut connection. It's actually not bolt, but as I said earlier, we have some threads here so that it holds the nuts. Opening this. Okay, so we have such a connection, and this piece can move in this direction, plus or minus. So if you move it a little more on the left hand side, you can like this can lead to some initial buckling of the beam. Maybe not for this one, but for this one you might lead to some initial bucklings like this, which may lead to some errors in your measurements. You have to make sure that there is no axial force, because the axial force means there might be further deflections, and you may have some measurement errors just because of this. Also, we have, I try to tighten the shaft on this side, on the ball and socket joint, with hex nuts. I guess they are called hex nuts, I'm not sure. So you have to make sure that as this rotates, the shaft rotates as well, but there might be some relative velocity differences between these when you suddenly increase the speed or decrease the speed. So due to friction, they will be quite close and they get to the same point at somewhere, but since it's dynamic at some point, this might be faster than this, and due to the friction, this gets to the speed of this again. But in the meantime, you're taking your measurements, and you may have some wrong measurements as well. So this is another. As in all the experiments, this experiment also is prone to errors by humans as well. Because, for example, one of you guys will be holding this measurement device, if you were here, and the other was controlling the speed. But the one who measures, takes the measurement, might move his or her hands left or right, up and down, which actually drastically changes your measurement, the accuracy of your measurement. And also, as I said earlier, this device takes the measurements thanks to the white stripe on this black strap. But if you move it a little bit left or right, the laser actually would go to the metal ball and socket joint, which actually reflects the light as well. So you will get ridiculously changing measurements. So these are some other measurement errors or roots of errors in this experiment. So thank you for watching the experiment, and I will send you the shaft parameters that you will use and the experimental measurements that I have taken, so that you can compare these values with your theoretical calculations and find the error percentages. Thank you.